Okay, so what's happening with cellular phones is, of course, there's been an enormous development over the last, I would say, 20 years, maybe soon 30 years of these cellular phones. So, of course, nowadays we have them for everything, and we get an enormous pressure on putting more and more communication systems inside of them, which, of course, needs more and more antennas inside of them. When we see some of development, of course, we have the early ones that sits really in the back here, which was a very big, bulky thing, which of course you can only talk on. Maybe you could start sending SMS in the later ones. And what you can see there is this antennas that really are sticking out. So we will look at a few of those. And around 20 years ago, we could see that these antennas disappeared, even if there is one coming up over there. It really went to this embedded antennas inside of the structure. And then the huge thing that's of course happened then around 10 years ago is that all of these ones basically became a screen. So some entertainment, communication, internet device that needs to use a lot of different ways to communicate, and of course have much higher bit rate and so on, and many more frequency bands, and much less space for the antennas. So it's a very, very tough environment to actually put in antennas inside of these kind of devices. Some of the results I take here comes from some overview articles you can see here, which is now a couple of years old. But what's happening in the latest years is that you cannot even see the antennas anymore. Everything is inside of these structures, which you can actually not even open without destroying them. If you go back in time, you could actually do anything. You can change pieces and so on. So it was easier to understand what actually sits inside of them. So if we see some of these phones in this era, we can see some more dimensions and structure of them. And if we go back a few years in time here, which now are quite many years here. So this is from 97, so 23 years ago. And a phone that day basically looked like this. Actually, these are all my phones, so it goes back to my history of this, where you could do basically nothing. You can send your phone calls and so on. The interesting thing for us is, of course, that you had an antenna on it. And those days, this was the antenna. So that was what you had. And actually, those days, these antennas were manufactured by a separate company. So they made really good money selling these kind of antennas, which worked very well on these kind of phones. One thing you can see with it, which is quite important in these cases, is that this is a GSM 900, so 900 megahertz. So single frequency. That's what it was for these ones. And when it comes to these ones, these antennas are really good. So you can see it doesn't stick out too much. It's quite small, but of course it sticks out. So it's very visible where the antenna is. And the radiation of these ones is basically from, I would say, a dipole. It's usually called a monopole, where this is the ground and this is the top one, which is a shortened than a monopole that sits there. So it radiates with both the ground plane here and this device there. That means it would in that case be a dipole. And then we move on in these times, and we can see for these ones until year 2000, these external antennas still sits there. If you go back then in time, you can actually increase here the frequencies of these ones. So this comes with two frequencies, so similar type here. And of course, if you had these ones, you can make it really good like this. And if you do it like that, it's really like a resonant, what to say, monopole type antenna that sits there. And this is then for the 900 band that you have in these cases. So of course, if you were out and you didn't have good coverage, you just improved your antenna. The big and the very challenging thing for these ones are to get in these frequency bands, because it's definitely non-trivial to get more resonances on these kind of devices. It's actually very, very hard to get it on this kind of monopole device. It's hard to get many frequencies. And then what's happening is, of course, the antenna starts disappearing, and then all the way we go here, there are no antennas. The number of frequency bands are, of course, slowly increasing here. So this has now 3 bands. It's not a big difference between 18 and 1900 bands. It was more Europe and US had slightly different frequency bands. But then it starts adding other things that comes here. So that comes in more type of communication systems, more type of frequencies. And in all cases, the screen is really increasing. So this is one of the earlier iPhones that sits there, and you can see that you have quite a big screen. Luckily for the antennas in these cases, you also have quite a lot of spaces like on the sides. So this one's, they have antennas more on the side sitting there, but these you leave on the side of it helps the design of the antennas. So we can see a lot of things is happening, of course, in the design of these ones, and we should look a little bit at the antenna sides of these type of phones. So if we see the trends that really are pushing a lot of it is very, very large screens. So when you do this kind of phones and you want to sell them today, you have these phones which basically have no space left for the antenna. So you don't have these bezels in some ways that sits around, and where you left a little bit side, for example, on the top and bottom. If you leave that, you don't have a screen there. The screen is really working like a metallic shield. So it's like a ground plane. You don't read it through the screen. And if you leave some part of it, you can have that in plastic, and you can actually read it basically from those pieces. So that can create currents on the screen and so on and make it ready. You want to have some free space to do your antennas. The thinner you make them, the harder things becomes too. It's harder to design the antennas, the more you push them down. And a big trend today is really to shrink the size, the thickness of them. Then you try to bend them and make them soft in some ways. This all screen, no bezels that really sits there, less space for it. And then, of course, a huge challenge in all of this one is what you want to put inside of them. So you more have go-to experience, you have more internet, and you have many types of antennas that sits there. So you get more and more frequency bands that comes in. So now the 5G is coming in, and that really adds a different type of antennas, because in one part of the 5G, you go to the millimeter waves. And the millimeter waves are, of course, so much smaller in wavelength, so you start to put arrays inside of these ones. And then they have to coexist with all the other old antennas that sits there. You have near field communication in them, so more an inductive coupling when you put them above each other. So more and more antennas in really a tougher and tougher environment sits inside of these phones. And if we look at some overview and the typical antennas that sits there, is the older one really had this external antenna, so some monopole that's sticking up, which means that it was a pure antenna design. So when you designed these antenna, you didn't have to care too much about this device. You cared a little bit, but it was mainly designing this piece and making this very good. When you design the antennas that sits inside of them, of course, it's more the co-design of the entire structure. So designing of these antenna depends heavily on the rest of the chassis that sits around it. The external antennas, you can really make this quarter wavelengths monopole, and that is the version when you pull this out. It gets a length here, which is like quarter of a wavelength that can stick out there. And then to make it shorter, you can make a helix version, which then is what sits inside of these ones, where you really have shrank the size of them to something like this. So you take a wire that would like to be like this length, and you make it shorter. And it means it's sticking up less in some ways. And of course, you pay a price for it because it gets smaller. So bandwidth starts to be an issue. It's much more sensitive for different things. When we go for the internal ones, the early ones that came, basically all of them were of this PIFA type. So these are the antennas that really was coming first. And we can say it's a huge, of course, consumer demand, you didn't want your antenna to stick out. So that could we really say like the form factor, the industrial design. But there are actually more things that comes in. To continue on the process of doing these type of antennas and add more frequency band is basically useless. You cannot really do it. It's extremely hard to design these type of monopole, shortened monopole antennas, which are resonant at specific frequencies. You need a matching network if you're going to do it. You can't do it really in the antenna. But by adding these internal antennas, you actually get more design freedom. You can bend the wires in more free forms, which actually can create these additional resonances, so you can get more different types of resonances in some ways. You can pick them to specific frequencies, and it's easier to add that in this little bit shaped version as you have than this external little cylindrical structure that sits there. Nowadays, many of these actually have some planar monopole type antenna, and that is due to this reduced size even more and the thickness. So the PFA actually doesn't really fit in modern phones anymore. They are too thin and too squeezed with other things in some ways. And then they are just combinations in some ways of each other. So it's hard to say what it is, because even looking at these type of antennas that sits there, it's not directly that you could say, okay, this is a PFA, and thinking what came this PFA from with the L and the F in some ways. It's derived from that one, and then it's designed and optimized to actually give you what you would like to have. But you still give it a name because it's coming from that family of antennas in some ways. Then when we add it, of course, then you need to do the rest. You need to have the Wi-Fi inside of them, you have a GPS, you have Bluetooth, you have near field communication, and so on. For example, in the antenna, you can see here, this is the one that goes for the Bluetooth that sits there. This is the little piece next to the other big piece. So that is the antenna, if you think for the frequency band you designed your patch for. That is a little piece that's coming out. That's responsible for almost making this resonant around 2.4 gigahertz. So a typical radiation pattern from these ones, if we go back to these ones and these ones that's sticking out, that are more this, what we say, dipole helix type that we have here. So if you think you have a dipole radiating here, it's in the center and it radiates a little bit more close to it from the edges. And when we put up a helix stub above these ones, you get something that is very similar in some ways. So it's quite similar in the way that it's in some ways a shortened dipole, and the rest of the body is the lower piece of the dipole. So quite similar in that way. And it has some effects. So if you think about both these ones and these ones that sits here, they tend to radiate in all directions. So if you think about these ones again, you put it to your head here, you have your antenna here. It doesn't shoot the radiation away from you. It really radiates everywhere around this one. It's like almost omnidirectional to where it is, which means that it doesn't radiate away from you. This is a stuff that you actually can improve, and you did improve with this PFA type antenna that sits there. So the PFA is more sitting out on one side. So you have this side here. When you put it to you put this one here, your patch PFA is here, and it tends to radiate away from you. And that is the radiation that you can see here coming out in some ways. So it's more radiation away from you, which of course is good, because that's where your base station should be, and that should take out your signal. It's not your head in some ways. So it's actually quite good to radiate away from you, which is an advantage then going also to this integrated type of antenna. When you go for this planar type monopole antenna, in many cases they can sit a little bit everywhere on this, but they tend to sit in the bottom side of it. So if you take these ones again, the main antenna actually sits in these ones down here. And that is the one that then radiate again a little bit everywhere, because this is so thin and it's more from this edge here, so it radiates out from that one. It means it radiates in both directions here. But then you can get one advantage again by putting it down here. You actually go further away from your head. And if you're further away from your head, you're less affected by this SARS and absorption and so on. So you need to incorporate that into your design, how this is going to work and radiate, because they're going to be used by someone. And when you do that, of course, you have different modes where you have to test your phone and how they radiate and so on. If you hold them in your hand, it's one thing. If you put it to head, it's a different thing. So different types of antennas that actually behave differently. And we can see improvements of this one. So it's not to say that these were so good. I mean, they were incredibly good as pure antennas, but they were also very limited. And they were limited in the frequencies that you can use, and also in this really, what to say, radiation that goes both here and there. You cannot get them to radiate in one way. And also, you cannot really make them go, downwards in some ways, because you want your antenna to stick up. It means it goes closer to your head in some ways. So if we look at the internal antennas, they are, engineering-wise, like basically masterpieces, especially if you think about these ones, to make them work both like this, and you pull them out and it should still work, and it's purely mechanical that sits there. So you have, of course, a combination here of some helix type structure, and then you have these things that you can pull out of that. And that is actually what's happening if you take these ones, you can pull it out. So you get this long wire that sits there, and inside of this one sits the helix. And actually this is a separate device also from the phone in this case. You can just separate them, or you could in those days. And the performance for these frequency bands is really in some ways excellent, but it can give a higher SAR value due to this omnidirectional radiation in some ways. And adjustments of these ones for multiple frequency bands, if it's above 2, it's really difficult. 2, you can kind of do. To do more, it gets more and more difficult. It's very, very hard to do that with this type of monopole or stub monopole type of antenna. They're hard to modify. If we look at the internal antennas, we really can start with this P-PHY idea, the planar inverted F antenna. And it is really one of the most popular one. And it can, in some ways, direct the radiation. So when you think about it, if you have the ground plane here, it tends to radiate out from these ones. So it's like your patch, it radiates away from it. The ground plane, in some ways, shields the user a little. In reality, of course, it's a finite ground plane and it's quite small. So, of course, it radiates also in the other direction. And you can put these either typically in the top or bottom of the phone. So most of these cases, when you have these, they are placed on the top, but they could also be placed in the bottom of the phone. And to do that, you would need some free space, and you also need some thickness to do it in some ways. You can create this multi-band performance by creating different kind of currents path, like in these ones that you can have one current dominant going like this and one current going like that, and they have different length. And if they have different length, you can create multiple frequencies in the same way for you who did a multi-resonant patch antenna. You can see you have 2 dominant different resonant lengths. Yeah, that gives 2 different resonances. And that's a multi-band antenna. And of course, in phones, it's not enough with 2. You need to create even more in these cases. But it's simpler to do that than the external monopole antenna. So if we look at one of the first ones of this is a Nokia version. One of the first actually that came with an internal antenna. And one thing you can see with it again, the size of this one is in total size, not so different from a modern one. Is look at the size of the antenna. The antenna is huge. It's really a big piece of this one that sits there. It's of course the internal pieces here coexist with many different things. So inside of this one, you of course put other type of good electronics that you need to use, and the acoustics of the speaker and so on. They can coexist in some ways. But the physical size here is actually very, very big. You needed quite some large to do this before you could make better both electronics and of course better designs in some ways. And again, here you can see that you have some kind of slot that sits here. So this is some ways where you have broken up these PIFA, and that can create these two different resonances, because you can then get different resonances along this PIFA that creates two different resonance frequency. And these cases, this was a 900 and 800 band. The same thing with this Ericsson or Sony Ericsson phone that I showed you before. Similar version, similar time that came. And again, here you see very clearly here that, yes, you have put some kind of slot where you just cut away this piece here, which means that the current in these cases, yes, it can float like this. It can also float longer like that. And those paths have different length, which create different frequencies in some ways. And this one was then for triple band, but in many cases, the 18 and 19 can maybe coexist, or they can be separated. It's different cases that comes. And then you have another typical piece here, which then can be more connected. I would say in this case, it was to the Bluetooth version. And when you think then of manufacturing of these, if we go back in time, you can think like, of course, you know, one company could live and actually doing this, making a lot of money selling these ones. There was a company called Algon, who did most of them actually in the world. It was a Swedish company. Then, of course, it moves to this internal antenna. Company doesn't exist anymore. And here you can more think that what you do to produce the antenna is actually just a piece of metal printed on plastics. So you can actually get those antennas by just sticking them to the rest of the frame. So that is what you see up here in this piece here. So that can be cut out somewhere, very cheap to make, and then you can just put it on the structure and you can actually make the antenna. This is a similar version, so a little bit newer, and of course doing those is then heavily based on simulations. So it came a time of these in the designs that when you designed these type of antennas, that was more hard trials and tests and less simulation based. And everything with these internal antennas starts to become heavily simulation based. So similar things what you've been doing in FECO is that you actually in computers design your antennas, you test them, you optimize them in some ways, and then you of course build them and test them. And in these ones, you see the same thing here with some metal sticking out there. And all of these type of older phones here, you could basically open up. I didn't have that one open, but there you can actually see the antennas. You cannot do that in modern ones. When you do this, and in the simulations, you really have to test a lot. So if you think about when you did your patch antenna, I mean, you had some ground plane, infinite typically, or you took your finite size, and then you designed your antenna that sits there. When you do it for the phone, of course, you need to also test different type of environments. So you simulate these ones together with different positions where you put in your head, you put in your hand, you hold it in different ways, and you should see that it really works. So you have different models of doing that, and you also measure them in these environments. So you have in some ways mock-ups of heads and hands that you measure the phone together with. And when it comes to the head, you have this SAR that we mentioned before, the specific absorption rate, which says how much power could be absorbed by tissue, and it's regulated how much that can be. And every phone that is sold and on the market has to be tested according to some standards to make sure that they are inherently compliant with these rules. There are also rules for this that's called HAC, which is hearing aid compatibility, which means that the phone and the electronics from it cannot interfere too much with hearing aid devices. That's also forced and has to be tested. It's regulated how that has to be done. And if you look at these ones, models and measurements are actually quite accurate, even those days. So you can see the near field of your device. These are measurements that you can see here, and here we have simulations for it. And basically what is the strength of the electric and magnetic fields that radiating close to your devices. If you see measurements, the comparisons is fairly good. And even this is more than 10 years ago. So we are pretty accurate in our, what you say, numerical modeling of these ones and the numerical simulations. It is fairly accurate to reality. But if you think again, you did also this in your course, and you can see that one of the hard things is, for example, the material parameters. So one of the issues that you have to redesign your antenna from the simulation that you've done is that the material parameters of this FR4 is maybe not so accurate. And that has been done in all kind of these designs, because you put them on some kind of plastic, there are materials there, and you need to basically calibrate what those are. And if you can get all of that correctly, your measurements and simulation agrees very well in most cases. So we are fairly accurate in this case, is what we get at. If you then think about how you should design something, if you did it with your patch, you can see the trick there was really to get out the 2 resonances. And a typical geometry here, if you want a dual resonance, so 2 resonances, is to really create this slot that goes in here. And it's then unsymmetric in these cases, so it can create some shorter path there, and it can has a longer path here. And since we have these different lengths of those ones, we can create 2 resonance frequencies. And then of course we can move these ones. So if you think about the slot here, moving it that way will then make them more equal, moving it the other way makes them more different. And by changing these lengths and widths, you can tune your resonances to the resonance frequencies you should have. And that can be some rules of thumbs, you can test this, but in most cases you simulate it, you see what's happening, and you sweep some parameters for it. This of course then creates 2 resonances, and on phones today it's not sufficient, you need even more resonances. And then you can make more complicated one. So for example, in the B case here, you can see that you have some length scale there, you have some length scale there, and you have another one going around here. So by then adding multi-slots, you can create more length scales in your small little PFA structure here, which then can create more resonances. And now you can not only go in here and think that you say, okay, I measure the length of like these ones, and that should then correspond precisely to my resonance. The world is not that nice, because these ones, of course, in the next case, sits on some ground plane, there is coupling to the ground plane, and it's actually heavily complicated. But that's taken care of in your simulation. The simulation software takes care of that. So it's more to have the idea how you can change the lengths, and you can do it sufficiently much, and then you can test it by simulating it and start understanding what's happening in these cases. Similar versions here is what comes in this C part here, where you can see that one of them is actually separated. So in these cases, it's basically a parasitic element. They don't need to be in electrical connection to each other because you have strong mutual coupling. So you don't sometimes need the metals to touch each other. They can be separated, you can still create extra resonances, and you can get the resonances that you would like to have. So if we then look at what's typically happening a little bit more modern type of phones, we should see if I have these ones. Nope, nope. Oh, here it is. I had taken it out. So this is in some ways a building version of this that is fairly accurate to some of the cases today, at least. That when you make the frame that you of course can build your phone around, on that one you can basically directly print your metal. So not that version that you saw with these ones where you can have some plastic, you glue it afterwards. You can actually put the metal directly on this frame, which is what you build your phone on. And in these cases, you can see quite a few antenna structures. So we see something here, we see something here, we see something here, and actually you see something big inside here too. And all of these are for different type of antennas and different pieces of this radiation that comes out. So if we see these ones, you have the top part typically here where the camera is, and this is then the bottom part of these ones. So this is the main antenna. So this is also a MIMO type, so it has 2 types of antennas. So it has a main part here, especially for the radiating part, and then can be more balanced in the receiving. And here you have another diversity type of antenna. And the diversity type of antenna, if you use it at here, in this case, would then be closer to your head, which could be then more restricted on power and so on. And the one below here is then further away, so less of the SAR issues with that. And here you have this big near field inductive piece. So this is the one that makes them communicate, you know, when you put them basically on top of each other, you can easily communicate, you can communicate with other devices which are really in the near field of the antennas. So it's not a radiating antenna, it doesn't radiate to the far field as these other antennas does. It's for the really strong mutual coupling between two coils in some ways. Here you have other antennas. I'm not really sure which one this is. It could either be Wi-Fi, probably it's a Wi-Fi antenna, but it could also be there's a GPS antenna inside of it. Bluetooth is probably sitting more close to the main antenna or somewhere. There's so many of these antennas that sits on these frames because there are antennas for everything nowadays. Yeah, this is just some focusing on this near field structure where you actually can see this coils going around these ones, sticking around that. So it's really a loop going around. So different ways that this can be manufactured. One way is to just take metal and stamp out the metal. So this is quite some early versions that you can see here. It's still used, maybe not for phones, but for other kind of devices, where you actually have a solid piece of metal and you can get out the pieces the size you would like to have. The version I showed you for this one is more close to this one, which is a flex film, which is more a softer material where you just have a banded metal. So think back again to when you did your own patch. This aluminum tape that you used is very soft, so you can actually bend metal in these cases. And of course, it means you can print this first in some specific shape, and then you can put it to the device you would like to radiate. It doesn't have to be phones. You can do it in Internet of Things and so on. You can have devices there where you can actually get out your, the shape of your antenna to perform as you should. And there are other techniques that come, some hot stamp, PCB trays and so on. You can do etching for them. And nowadays you can even do, laser removing. You can have metal, you can have lasers, robots moving on and so on, either adding metal or removing metal from them. You can get a lot of advanced ways to actually get the metal in the way you would like on this kind of radiating devices. If we see some of the challenges that happens, is really that we have to support an increasing number of frequency bands. This is more to, in some ways, the communication electronics behind it. It's not as bad for the antennas, but we can see that in every generation of communication, there comes new frequencies. And if you add more frequencies, you need antennas, you need electronics that take care of them. We sit on this thinner, and nowadays, I think you have all seen it, it starts to be trendy with flexible structure. So these foldable screens are coming now, where you can take the screen and you can really fold it. It starts to also put a lot of challenges for the antennas. We sit in this all screen or bezel free versions. So instead of having a design like this, which is still very common in phones, the trend is really to make the screen sticking out everywhere. And that means that there are metal everywhere on this. So you leave very little space in some ways for your antenna. The only thing you basically leave on the side, the edges here. And the edges are not that big. And you need many different types of antennas. So they need to coexist on this little space to make all of this frequency works. And also the multiple input, multiple output, the MIMO. So you need more than one of them. So of course we need additional antennas for this. Adaptive matching is something that is coming. There's a lot of work on it. It probably exists in some prototypes and phones today, that you can actually rebuild your antenna according to the situation. Because if you imagine that you have your phones again on this, and then you put your hand on it, you detune the antennas. Maybe they don't work anymore. Then you can have a matching network that can basically fix this. So you can adapt for example, you as a user, you can also have matching network that change between different frequencies and so on. And then higher frequencies are coming. For a while, it was ideas around 15 gigahertz. Now the main trends is around 30. So for example, 28 gigahertz is really coming now. There is also ideas to get in 60 gigahertz ones, and all of this goes under these names of millimeter waves. And that means again that you have these devices, and then you have to start putting in some millimeter wave antennas there. And that of course takes its own space, even if the wavelength is small. In this very clouded environment, it starts to of course add more antennas that take space. And some view what this can look like. This is also an early prototype of 28 gigahertz. This is, I think, 3 years ago. So a lot of tests, because of course now you shrink the size. The wavelength is now 1 centimeter, if you think 30 gigahertz. And that means half a wavelength is 5 millimeters. So actually there's a lot of space. So in these ones, you can actually add antennas which are full size antennas that you cannot do at 900 megahertz or 600 megahertz. They have to be electrically small antennas. But here you have really the space that you need. You can really make them like a regular patch antenna, as you see here, because you have your dielectric that makes it even smaller, so a few millimeters in size. They fit quite a few in some ways. So you can test different types of antennas, and it means you can really fit arrays inside of this. And you can have arrays with approximately lambda over 2 spacing, sometimes slightly larger and so on, but over that order, you can really fit inside of them. And I think I showed you this one also with an array. This is from a more recent phone. So some Samsung phone in these cases, where you can add modules. So of course, when you come as a user, if you put your hand above your millimeter antenna, it won't radiate. So then you can of course put different of these millimeter devices on different places. So at least some of them work. If more works, they can work together. So that is good. So here is some different configurations, for example, putting them on different sides of it and filling them with different type of antennas. Obviously, this is some combination of some patch and some dipoles, which then have slightly different radiation patterns and so on. So some of them can radiate more in one way, and then maybe the other one slightly broader. And you can get an array, so you can have different, phase steering of them, so you can actually steer the beam in different directions. Because when you go up to 28 gigahertz, the distance to the base station in number of wavelengths is increasing, so you get an increased free space path loss and so on, which means you can compensate that with an array factor. So you can get a higher gain of these antennas as using them as an array. So that's really coming into our devices today. And it is out on some markets, and it's coming probably broadly out in 2021. So more markets is coming out. I don't have it, for example, today. So that is some parts of this terminal type of antennas, where we really see that there is a lot of antennas that comes in these devices. And now I only talked about basically cellular phones. Of course, we have similar things when we sit inside of basically our computers. Inside of the computers, that sits different type of antennas. Find them here. Of course, if you go to your laptops and so on, you have more space. So of course, in your laptop, you can actually fit better antennas, typically patch antennas, or you just couple to the big pieces of metal that sits there, and you can actually get quite good, easily get quite good antennas. But nowadays, there also comes a lot of this Internet of Things and a lot of small sensors, and a lot of those devices, of course, need antennas. And they can be quite small in some platforms and can be very challenging on design. Okay, so this is basically the last lecture in this course, which means that we covered at least some new materials, even if it's more an overview type of lecture. And in the next lecture, which is the one on Thursday, it's more repetition. So on that one, I will compute or calculate a test exam. So it's already uploaded on Canvas, So it's very good if you take a look at that one before the lecture. So I will go through it during the lectures, solving the problems, and of course use this as a repetition of the entire course. On Wednesday, we heard also the last exercise. And that is in some ways the really last chance for you to ask questions. We have the final coming up, I think January 12, I think it is. I'm not entirely sure. You have to see on the homepage. And there we don't have really any lectures before that. So make sure you utilize these exercises that we have to ask questions. Things that you have not understood or confusing things somewhere, take the chance. You have the chance to ask whatever you would like on those exercises, that exercise that's coming up. We have a quiz, which is the last one. It's closes actually in 1 week. I extended that until next Monday. So it's closing on Monday. So do that one. And if you've done those 6 quizzes, you can get some bonus points for the exam in January. If you have missed one of them, there is a repetition quiz that's opening on Thursday. And that can compensate for that you have missed one of the quizzes that was before. So if you missed some of them, do the repetition. If you didn't miss them, you did them all, still do the repetition. It's a good way to actually get the repetition of the course because it goes through all the other quizzes we have had. It picking randomly 2 problems from each quiz. So if you do that and you feel that is, you understand that, yeah, that is good. Then you have actually understood those pieces of the course, which is quite a big part of the course. The final report of the laboratory sessions will be advertised since we now have postponed the last lab for half of you until January. We will come up with new dates for that. And also the dates where you can sign up for those labs. We have discussed it, and probably it will be the week after the exam, which means it's the first week of the new semester for you. So probably we'll add the labs there. We will also check there in your schedule so it doesn't crash with too many of your other courses. Okay, so I would say that is it, and it's also 3 o'clock. So I will